So let's talk a little bit about dating planetary surfaces. Oh, first, let's look at a few pictures here. So let me just pull that up, and we can just walk through a few of these pictures from the textbook. This is a composite created by the Mars Curiosity rover in 2012. That's a nice, pretty picture of Mars. Here's a little picture from Apollo 15 mission on the moon in probably 1973 maybe, or 72. Here's a nice picture of some of the dwarf planets. The orbit of all 8 planets, they're in blue, and then the red ones are the dwarf planets, and you can see they're getting farther and farther off the beam a little bit. They're more like the behavior of comets. Here's a nice picture of Mercury. It looks a lot like the moon. It's heavily cratered and doesn't have much geologic activity. Geology on planets erases craters. And so if you've got weathering or volcanoes and earthquakes and stuff like that, but dead planets tend to show their craters. And so one way to know how geologically active a planet is just to look for craters on it. Doesn't work as well for these guys, the giant planets, because they're gaseous on their surface, so they don't have craters. Notice the Earth in the bottom here is shown for scale. Here's a nice picture of Pluto. There's Saturn and its rings. Here's an asteroid. Asteroids are also heavily cratered, as you can see there, for the most part. There's a comet. These are 2 popularizers of science. On the left is Carl Sagan, on the right is Neil deGrasse Tyson. There's a nice picture of Jupiter taken by the Cassini spacecraft as it was going to Saturn. Here's Jupiter's moon Ganymede. This is the Levy-Shoemaker comet that was hit Jupiter in the summer of 1994. Those are the places where it hit. It just happened to do the hitting right during the weekend of my wedding when I got married. Here's our moon. Now we get to what we're going to talk about now. So let me switch back to the text. And so we're talking about dating planetary surfaces and how to tell if a planet's surface is old or young. And one way is just what we're talking about. You can look at the surface, and if it's heavily cratered, it's an old surface, because that means the craters haven't been erased, and that usually means it's been that way for a long time. What we mean by old or young for a surface is how long since it's been sort of erased or eroded or something like that. The rock on its surface has been changed in some significant way. And so heavily cratered objects like the moon are very old. The Earth has a very young surface because it's constantly changing. We have a biosphere that changes the surface. One way we age rocks or surfaces is with called radiometric dating. It's where radioactive materials, and we name them by these are all elements in the periodic table you might not have heard of, but they are samarium, rubidium, thorium, uranium. You've probably heard of uranium, and potassium. That's one you've probably heard of. And they're called, they decay into a different product. This is, so the samarium decays into neodymium, rubidium decays into strontium, thorium decays into lead, uranium decays into lead, and potassium decays into argon. You probably heard of the last few of those. And this is called the half-life. That's how long it takes for half of it to decay. And these are in billions of years. So the samarium decays in 106 billion years, rubidium decays in 48 billion years. That's the half-life. Thorium is 14 billion years, uranium is 4.7 billion years, and potassium is 1.3 billion years. So if we really want to age a surface, ideally we just go take a rock from its surface and date it using this radiometric technique. But we can't always get rocks from surfaces. We don't visit all of the planets we see, and we certainly, even if we do visit them, we don't bring rocks back from them. Usually, like on Mars, we haven't had anything come back from Mars yet, although we're working on that right now. Usually we just send something there and leave it there. And so I'll give you an example of radiometric dating. The one we just talked about was uranium-238. By the way, the 238 is its atomic weight. So uranium has 92 protons. And so that would be like 146 neutrons, because that has to add up to 238, right? And so protons plus neutrons equals the number here, the 238. That's what that is. And its half-life is 4.5 billion years. And what that means is if I have a pound of uranium, then in 4.5 billion years, I will have half a pound of uranium I think it was lead-206, wasn't it? I'm going to assume that's what it was. Because the uranium decays into the lead. And so then in 2 half-lives, so in 9 billion years, I'll have a quarter pound of lead and 3/4 of a pound, a quarter pound of uranium, and 3/4 of a pound of lead, and so on. Each time, each half-life, I have half as much of my parent material as I did 1 half-life ago. It divides in 2 for each half-life. And so the half-life of uranium-238 is 4.5 billion years. So in 4.5 billion years, I have half as much. In 9 billion years, I have a quarter of what I started with. In 13.5 billion years, I have an eighth and then a 16th. Each half-life cuts it in half. Usually they say your material will last about 10 half-lives before it's too hard to tell. That means it's down by a factor of about 1,000 in 10 half-lives. And so you basically have no material left, or it's so small it's hard to measure. And so you might think, well, how do you measure the half-life of something that has a half-life of 4.5 billion years? You can't just set it on a table and wait for 4.5 billion years. Well, it turns out that you don't have to, because if you look at, for example, in this case, let's say 9 billion years, so let's just say 4.5. In 4.5 billion years, there are about 2.5 times 10 to the 17th seconds. There's 4.5 billion years times 365 days per year times 24 hours per day times 60 minutes per hour times 60 seconds per minute. And you multiply all that together and you get about 2.5 times 10 to the 17th seconds. Right? But there are about 6 times 10 to the 23rd atoms in a pound of uranium-238. Sorry, I had this number wrong. This is 1.5. And so if you divide the number of atoms by the number of seconds here, it means, I had to change this one too. This is about at this rate, 6 times 10 to the 23rd atoms in 1.5 times 10 to the 17th seconds is about 4 million decays per second. And so it's easily detectable. So you can figure out the rate of decay and convert that into years per pound, and it comes out to 4.5 billion years for the half-life. And so it's not very hard. Even though these half-lives look really large, they're easy to measure because atoms are super tiny, and so there's zillions of them in a small amount of material, and so the half-lives are easy to measure. We have things called Geiger counters that are very good at measuring those. We use radioactive materials for all kinds of things. You need radioactive materials with very long half-lives, like I was talking about earlier, like rubidium and potassium and uranium, for very long half-lives. But also we use, for example, carbon-14 to measure archaeological ages, human-related or organic material ages, because the half-life of carbon-14 is about 5,000 years instead of 4.5 billion years, and so you can measure shorter time period events with things like carbon-14. We're very good at this. It's been understood for a long time. So we measure these. So if we get a rock, we can pretty much measure how old it is pretty easily, and how long since the last time it was melted. You can pick up a rock on Earth, do some radiometric measurements on it, and tell how long it's been that rock that it is, or since the last time it was melted. And so we can do that on the moon and other places where we visit and bring back rocks, but we can't do it on places where we're not bringing back the rocks. So what we do on those places is we look at the crater density. Oh, let me just pull up this picture really fast. There we go. So this is a picture of a material that it starts out all uranium or something like that, and then gradually half of it decays, and then a quarter of it's left, and then an eighth of it's left, and a 16th of it's left, and a 32nd of it's left. This is just the number of half-lives, so that's how it gets. That's how it decays as it goes along. Right. So what we do for more distant objects that we can't really get rocks from is we calibrate them against the moon. Since we've been all over the moon kind of at different times, we've collected rocks, we can look at the crater density on the moon and then use radiometric dating to tell how old that surface is right there. And then we can look at the different cratering densities on the moon and calibrate them. We can say, oh, the rocks from this region are this old and has this density of craters. This rocks from this other region are younger and it has a lower density of craters. And then we can just use cratering rates to determine the ages of surfaces on planets we don't land on, so like the moons of Jupiter or Mars or Mercury and so on. And so we use radiometric dating to sort of calibrate the moon's crater density versus age, and then we look at cratering density on other planets to learn how old their surfaces are. Eventually, we'll be able to bring rocks back and check how accurate our answers have been for that. But we're not doing that yet. Soon on Mars. So the last section here is talking about the solar nebula and how we want to figure out how the sun formed. And so there's lots of clues in how our solar system looks that tell us how it formed. For one thing, all the planets move in the same direction, orbit the sun in the same direction, and they're all kind of rotating in the same direction for the most part. And so that tells us that they're all they all have the same angular momentum, and that fits certain explanations for how the solar system formed and not others. The composition tells us a little bit about the composition of the cloud that formed the sun and the planets. The inner stuff is rocky and metally, the inner planets, and the outer stuff is icy. And it turns out that a hot sun doesn't let ices form. And so the compounds I was talking about in the outer planets, like water and ammonia and methane, they're all gases in the inner solar system, and they can't clump up and form solids the way rocks can. Rocks can form solids even at pretty high temperatures, and metals can form solids at even higher temperatures. And so in the inner solar system, the things that formed clumps that could then gravitationally get bigger and snowball into bigger and bigger objects were the rocks and the metals. It was only when you got really far from the sun, out where the Jovian planets are, that it was cold enough that compounds like ammonia and methane and water could form solids. And then those could clump up. And of course there was much more of those because there's more of hydrogen than anything else. And so those hydrogen compounds like water, ammonia, and methane were very plentiful, and they could form solids out there. And so those planets were able to form from the enormous amounts of water and methane and ammonia and other hydrogen compounds in the outer solar system, where the inner solar system wasn't able to do that because it was too hot. So the current model for the solar system is that the solar system formed from a large cloud of gas and dust that all had some sort of initial rotation. that that the angular momentum of that rotation carries forward today in the planets and smaller objects all orbiting the sun in roughly the same direction. We can see the same type of thing happening now in extrasolar systems. Now we see planets orbiting other stars, which we didn't see 20 years ago, and these seem fairly consistent with our understanding of how our solar system formed. Basically what happens is these large clouds of gas and dust cool off, and the particles, the gas and the dust, form larger and larger clumps that collide and stick to each other as they cool off. Gravity kind of pulls them in. The lion's share of the material gets pulled to the center, which forms a star, and the outer materials, if they're spinning, if they've got enough angular momentum that they can't fall in, then they form planets, or what we call planetesimals, which are sort of pre-planets, large objects that are smaller than planets. These collide and eventually accumulate to form planets. If you look at the surface of the Moon and Mercury, you see enormous craters. These happened at the end of the cratering era, and these are planetesimals, large objects that were colliding with the surfaces of these planets at the end, sort of the end of the formation of the solar system. And so we see lots of evidence for how the solar system formed in what we look at as we look around the solar system.